Thank you for attending our first webinar series. We're trying to launch a series that's based on two of our research projects together with University of Vermont, McGill University, and York University. One that's in its 6th year, Economics for the Anthropocene, of which Tim is part of the 3rd cohort of PhD students, as is Kelly Hemshaw, our second speaker. And a second project's in its 2nd year called Leadership for the Ecozoic. So Tim is a PhD student at McGill, as part of that E4A group, and he's going to talk to us today about all things energy. So Tim, take it away.
Okay. So firstly, I think we've all seen a lot of headlines like these ones here. So we all know that renewable energy, it's becoming better, it's becoming cheaper, it's taking off exponentially, and it's disrupting the fossil fuel incumbents. So this is the pervasive story that's out there. And I think that the broader story that's being told is that we can have an industrial economy and modern global society based on clean renewable energy, and we can do it relatively quickly. So it's very easy to believe this story. I think it plays into our confirmation bias. It sounds positive, we want to believe it. But what I want to suggest is that there are some risks to viewing the future through one narrative. And I'll explain what I mean by that a bit more. So my name is Tim Crenshaw. I'm based in the Department of Natural Resource Sciences. I'm in the 3rd cohort of Economics for the Anthropocene. And my research is all about energy, specifically the dynamics of the global energy system and its transition towards renewable energy. So why am I doing this? I've always had an interest in energy. I have a background in the physical sciences, and I tend to be skeptically minded. So I tend to think that if something sounds too good to be true, it probably is. And for me, this is not just a curiosity. I think it's really hard to overstate the importance. What's at stake here with the energy transition? If we can't secure a sustainable energy system, we don't really have a future as a society. And given that's the case, I'm not really satisfied with some of the simplistic narratives out there. So ultimately, what I want to answer, the basic question is, does industrial civilization have a future? I know that sounds a little ominous, but I think it is an important question to ask. Yeah, future. So this is showing where we are currently. This is total primary energy supply going back to 1900. We are using an enormous quantity of energy. It has increased 26 times over this period. We're now using over 13 billion tons of oil equivalent per year. So we've created a monster. Despite a lot of those optimistic headlines, it is still 95% non-renewable. And solar and wind, the two energy sources with the greatest growth potential, make up less than 2%. It is on the cusp of major change this century due to the need to reduce emissions, to tackle climate change, alleviating energy poverty in many developing countries around the world, and also issues related to resource depletion. So the global energy system, it is the cornerstone of the global economy. There are some deep links between available energy and societal complexity, or the types of technological, political, social arrangements that we can achieve. So this runs very deep. The transition to renewable energy is historically unprecedented. We've never done anything like this. And that's why we have to be very careful asserting how it might unfold before we've really begun the process. It's not just an engineering challenge or an economic challenge. It is what system scientists would call a complex, physically bounded, path-dependent socio-metabolic process. The energy system consists of non-substitutable distinct energy carriers, such as electricity, heat, and liquid fuels. And because these have very different properties and are used in very different ways, we can't simply aggregate them into a common pool. And that's very important when talking about renewable energy. Energy is strongly autocatalytic, meaning that it takes a large part of the output of the energy system to maintain and operate the energy system. This is not true of many other commodities, such as fish or wood. So energy is special in a way. And this creates the risk of a net energy trap, which is what would happen if available net energy became insufficient to deliver all non-discretionary energy services required by society while growing and maintaining the energy system itself. So what is the current state of energy modeling? There are a number of energy models out there used by the International Energy Agency, the US Energy Information Administration, a variety of different integrated assessment models used in climate modeling, and also many economic analyses of renewable energy. They tend to make some common errors. Energy is treated as homogeneous, both in type and in quality. The issues of path dependence and a life cycle view of the process is often ignored. There's the inclusion of many speculative technologies which haven't yet been proven. And there's also missing aspects that would tend to make things more difficult, such as supply constraints, associated infrastructure change, and a variety of balancing feedbacks. So this is really a problem of reductionism. According to Giampietro, this represents a clash of reductionism against the complexity of energy transformations. So a lot of these studies have as much in common with the real energy system as this mechanical duck has with a real duck. It just doesn't really capture the true complexity involved. This is a very simple high-level overview of how most mainstream studies look at the energy system. So it's relatively simple. We have a number of different primary energy resources, both renewable and non-renewable. These flow through to various types of secondary conversion, which produce energy carriers, which are used by various types of end-use capital to provide necessary energy services. So what I'm adding to this picture, which I think is often ignored, is a disaggregated view of energy carriers, treating these as distinct and non-substitutable. Flows of these energy carriers both into the production of primary energy, which is known as the autocatalytic loop, and also the maintenance and turnover of end-use capital, which is known as the capital hypercycle. There's also the fact that primary energy resources exist on a quality distribution. They're not homogeneous, and we have largely produced the highest quality resources so far, leaving the lower quality resources for later. And over this entire picture, there's a large degree of irreducible uncertainty. So my modeling approach is based in system dynamics, which is essentially a feedback-rich system of equations. This is what the interface might look like. There are a number of different software packages that are used for doing this type of modeling. Mine is a physical model. So I'm specifically looking at physical aspects only, no political or economic constraints. And as such, it's going to produce the best case outcome in terms of what's physically feasible. It involves endogenous decision making. There's an algorithm within the model which is able to take in information about the state of the system and guide its evolution over time in the best way it can. So it doesn't have to be told what to do externally. It's an exploratory model. It's not predictive. It doesn't pretend to predict the future. Instead, it outlines an envelope of physically feasible transition pathways. So that's what we can realistically work within. And it's based in Monte Carlo simulation. So to explain that further, Monte Carlo simulation is where inputs that are fundamentally uncertain are varied and the process is repeated in order to build up a profile. So for example, for all uncertain inputs into this systems model, a probability density function is created for each of the uncertain inputs, and a point on these distributions is chosen at random. Those inputs feed through to the dynamic model, which is simulated to produce an output. And this process is repeated over and over again until we've built up a profile of different outcomes, different ways that the system can behave. And these outputs can be categorized. For example, here, the lower group might correspond to what I've called the net energy trap. So let's take a look at some results. These are mean model outputs over 1,000 simulation runs. So first, primary energy supply coming from renewable sources. We have Biomass increasing strongly. So that's things like biofuels, burning wood, various types of crops used for energy purposes. We have strong increases in geothermal, and those tend to reach their limits, their approximate limits by around mid-century. And other sources such as solar, photovoltaics, and wind continue to increase, but at a much lower level. Energy carriers. So because the model quickly eliminates inefficient uses of energy, there is an initial large reduction in both liquid fuel and heat consumption. And over the century, there is a strong shift towards electrification of various end uses. So electricity tends to increase. Liquid fuels and heat, they bottom out by mid-century, but then they slowly start to creep up again. So there are many aspects of end use that change, but one of the bigger ones is transportation. So the model very quickly eliminates internal combustion engine cars, so conventional cars, and also other heavy vehicles using internal combustion engines. And it replaces this transportation service with electric rail and also diesel electric rail. So there is a strong shift in transportation modes. So in terms of non-renewable primary energy supply, this shift in the way we use energy leads to a decrease. So we can decrease oil, natural gas, and coal consumption until around mid-century, and then things become a bit more tricky. There is a strong resurgence in most of the model runs in coal and gas, and this is because oil by this point is so heavily depleted that it's necessary to turn coal and gas into liquid fuels to meet residual liquid fuel demand. So that's something that the mainstream has almost entirely missed. So in terms of the renewable share of total primary energy, this can increase, and it can increase quite quickly up to mid-century, but then it really struggles to get beyond about 40 to 50%. It doesn't seem like the system can exceed this level. So some high-level conclusions. What we can do, we can achieve major emissions reductions by mid-century. One of the most important parts feeding into the model is demand, what we're doing with demand, and we can vastly improve our prospects by rethinking demand. We can buy a lot of time for deeper changes that are needed in culture and behavior. But there are some caveats here. We probably can't reach 100% with current technology. It doesn't seem to be physically possible. Reducing emissions after 2050 will be increasingly difficult. If we want to constrain some of the higher emissions technologies, such as conversion of coal and gas to liquid fuels, then we increase the risk of falling into a net energy trap. So the baseline risk of a net energy trap is approximately 10%, and that increases strongly the more we constrain emissions. So there is a trade-off here between emissions reductions and risk of falling into a net energy trap. So a feasible energy transition is not guaranteed. I think that's important to underscore. So what can we do? Overall, we can avoid taking common energy transition narratives at face value. So as appealing as they may be, I think we need to apply a healthy dose of skepticism to these. It tends to be more productive to focus on demand rather than supply. So in order to shift the outcome of the model, we can reduce demand. We can promote flexible energy consumption habits, so aligning our consumption with renewable energy availability. We can move away from inefficient technologies, such as private vehicles, towards more mass transit, and also electrification of many end uses. And we can build a sharing economy for energy. This is one of the most important aspects, is that the provision of energy services at the moment is highly individualized. And by shifting to a more public provision model for energy services, we can make some major gains. I think we need to strengthen energy systems at the local level. Resilience is key here. We can't rely on centralized systems for providing energy services to remain viable for the long term. we have to recognize energy transition as a complex, physically bounded, path-dependent socio-metabolic process. So we really need to avoid those reductionist narratives. And finally, we need to ensure realistic expectations of energy transition inform broader social and economic change. So we can't let the simpler narratives inform the way that we talk about these issues going into the future. Okay, that's it.